Hello there. Recall that in a previous video, we learned about continuity at a point. To determine if a function f is continuous at a point, say a, we check if 1. F is defined at the point a, or that is, f of a exists. 2. The limit at that point exists. And 3. These two are equal. So in this video, we'll be discussing the concept of one-sided continuity. The conditions are the same except that we replace x approaching a out here to a from the left or a from the right. So it's like taking one-sided limits instead of just the limit. So to understand this better, let's have some examples. Starting with the first example. So in here we are given f of x to be equal to 2x minus 1 if x is less than or equal to 0, or x plus 1 if x is greater than 0. Our goal here is to find check the one-sided continuity at this endpoint of interval, which is x equals 0. So before we solve this, feel free to pause the video so that you may try this one first on your own. Okay, good, so let's start. So again, to do this, we just check the conditions of continuity, just replacing the limit with one-sided limits. So we'd start by checking the value of f of 0. To do this, what we'll be using is this part out here. Since at x is less than or equal to 0, x is equal to 0. So x is equal to 0 is in this interval. So we'll have 2 times 0 minus 1. And so 2 times 0 would just cancel out. So we'll have 0 there. And so we'll be left with negative 1. So this is the value of f of 0. Let's now move on to checking the limits from the left and the right. Starting with the limit from the left. So with the limit from the left, we'll be using this one out here, since the values from the left of 0 are negative or less than it. So we'll have 2x minus 1 out here, and then since this is just a polynomial, we can just plug in 0 out here. So we'll have 2 times 0 minus 1. So we can disregard the sign out here. And so we'll have negative 1. So the value for this one is negative 1. For the limit from the right, we'll be using this one since values from the right of 0 are greater than it. So we'll have the limit of x plus 1 as x approaches 0 from the right. And then since this is just a polynomial again, we can just simply plug it in. So we'll have 0 plus 1. We can disregard the sign again. This is just a polynomial. And so we'll have 1. So we'll have 1 out here. And as you can see, these two are equal while these two are not. So we can conclude that f of 0 is equal to the limit of f of x as x approaches 0 from the left, while it is not equal to the limit as x approaches 0 from the right of f of x. So since we have shown all three conditions, we can now conclude the continuity, or the one-sided continuity rather, at x equals 0. So given this one out here, we know that f is continuous from the left at x equals 0, while this one out here, we know that f is discontinuous from the right at x equals 0, since it is not equal, while this one is equal. So this is the one-sided continuity for f at x equals 0. And to verify this, indeed, if we check out the graph, as you can see, from the left, out here, the limit matches the value of the function, while from the right, it doesn't match the value of the function since this one is the value of the function at x equals 0. So it is continuous from the left, while it is not continuous from the right, or discontinuous at the right. And so clearly this out here is the final answer for this example. So I hope you got that one correctly. And let's now move on to the second example. So we have g of x equals the square root of x minus 3. And our goal is to find or check the one-sided continuity at x equals 3. Before we solve this, feel free to pause the video so that you may try this one first on your own. Okay, good. So let's try this one out. We just check the three conditions again. So checking g of 3, the first condition. So we simply plug in 3 in this one. So we'll have the square root of 3 minus 3, or when simplified is square root of 0 or 0. Next, we check the one-sided limits, starting with the limit from the right, then the left. So the limit from the right, we know that to check the limit or the one-sided limit given a radical function, let's try to understand what happens when we plug in this one in here. So we'll have this. Take note that the values from the right of 3 are values like 3.00001 minus 3. And since we know that this one is greater than this, we know that this value approaches 0 or is equal to 0, but a positive value, since again this is greater than this. So we'll denote that by the square root of 0 with a positive sign out here to denote values from the right of 0 or positive. So we know that when we take the square root of this one, the outcome is simply 0 since this one is positive. So values very close to 0 but positive. So the value is defined. And so the limit for this one is equal to 0. On the other hand, for this next one, so we do the same process. So we'll have this and observe that the values from the left of 3 are values like 2.9999 minus 3. We know that this value is equal to a value close to 0, but since this one out here is less than 3, then we know that the outcome is a value close to 0 but negative. So we'll have here the square root of 0 with a negative sign to denote values close to 0 but from the left of it, or negative values. And so we know that in radicals, in even radicals to be exact, the expression inside must always be positive. And so this one, since we know that this one is negative even though it is close to 0, we know that this value is undefined. And so we say that the limit does not exist. So given this two, we can now determine the one-sided continuity at x equals 3. Observe that these two are equal, or g of 3 is equal to the limit as x approaches 3 from the right. So we conclude that g is continuous from the right at x equals 3. On the other hand, this is not equal to this clearly since this one does not exist. So since condition 2 isn't satisfied for the left of x equals 3, then we say that g is discontinuous from the left at x equals 3. And so this is the answer for this problem. And if we want to verify, we can check out the graph, and clearly in here, observe that the limit from the right matches the value at x equals 3, while on the left, even though there is a value out here, there are no graphs or curve from the left. So clearly, it is discontinuous at the left since, again, the condition 2 isn't satisfied. And so again, for this problem, this out here is clearly the final answer for this one. And now let's move on to the last example. So in here, we're given h of x is equal to the greatest integer function of x, and our goal is to find or check the one-sided continuity at x equals 1. So before we start, feel free to pause the video so that you may try this one first on your own. Okay, good, so let's start. To do this, we first recall that the greatest integer function of x is given by this piecewise function out here. So this extends to infinity. So it's given by this, or essentially, this means that the greatest integer function of x is equal to n, wherein n is some integer, if x is from n to n plus 1. So this just tells us that it's like all values just before the next integer, in this case n plus 1, is equal to the previous one, which is n. So if you are still having a hard time understanding and grasping the idea in this function, I have a video out here wherein we try to tackle greatest integer functions and applied it on the concept of one-sided limit. So you may check that one out first. And continuing, let's now apply the three conditions of continuity, or one-sided continuity in this case. So we first check the value of h of x at 1. So that is h of 1. Oops, take note that I had a mistake in this one. This should be h, and the following examples, or the following slides, f out here should be h. So just take note of that one. So this one, so we'll just be using this part out here since we have x equals 1 out here. So we'll have this 1. Now we check the limit from the left and the limit from the right. So to do this, first we start with the limit from the left. So take note that from the left of 1, those are values less than 1. So we use this part out here. So this one will be equal to 0. And since this is just a constant function, the limit is equal to 0. And we do the same for the right of 1. So for the right of 1, we use this one since values from the right of 1 are greater than it. So the greatest integer function of x becomes 1. And since this is just a constant function again, we just use 1. And so now, observe that these two are equal while these two are not. So then, we can conclude that f is continuous. Again, this is just h, so just disregard that one. So h is continuous from the right, since these two are equal, while it is discontinuous from the left, since these two are not equal. So this is the one-sided continuity for h at x equals 1. And indeed, if we check out the graph, you can clearly see here that at x equals 1, from the left, this one is not, or discontinuous, since the value of the function is this one. So this one is the f of 1, or h of 1 rather. H of 1. So from the left, it doesn't match this one, so it is discontinuous from the left, but from the right, it is continuous. So this out here is clearly the answer for this problem. So I hope you got that one correctly. And yeah, that's the concept of one-sided continuity. I hope you enjoyed and learned a lot from this one. Apologies for a lot of audio interruption in this video. So it's beyond my control. But I hope you got the message and the lesson clearly in this video. So yeah, that's it, and that's all for this video.